Hello friends, the topic of today's discussion is retrosynthetic analysis. It's a very important topic of organic chemistry. Please watch this video till the end. This will enable you to learn basics of retrosynthetic analysis. Retrosynthetic analysis requires knowledge of reagents and organic name reactions. You all must be aware of several reagents, organic name reactions and their applications. If you know the applications of reagents and organic name reactions and someone asks you A reacts with B in a particular solvent under the given reaction condition to produce C, then you can easily predict the structure of C. For example, suppose someone asks you to predict the structure of product when acetophenone is allowed to react with sodium borohydride in ethanol at 0 degrees centigrade to RT. Here, we know that sodium borohydride is a reducing agent that will reduce keto group to alcohol. So, we reduce the keto group of acetophenone to alcohol to get the structure of the product, which is 1-phenyl ethanol. Similarly, if we are asked to predict the structure of product, if benzyl bromide is allowed to react with sodium thioethoxide in DMF solvent at RT, then we know that sodium thioethoxide is a nucleophile, so it will attack on benzyl bromide via SN2 mechanism to produce benzyl ethyl thioether. The situation becomes a bit difficult when you have to synthesize a product molecule which has a fixed and unchangeable structure. In that situation, you have to work backward towards the starting material. This process is called retrosynthesis, and the art of planning the synthesis of a molecule is called retrosynthetic analysis. Synthesis of a target molecule may involve one or more than one steps. Here, we will first learn the retrosynthetic analysis of one step and after that for multiple step synthesis. Let's first learn different symbols and terminologies used in retrosynthetic analysis. Let's first talk about retrosynthetic arrow. This is an open-ended arrow. The general meaning of this arrow is can be made from. Let's have a hypothetical reaction in which A reacts with B to produce product C. The retrosynthesis of this reaction can be represented as C retrosynthetic arrow A plus B. This means C can be made from A and B. Let's have a real example. Benzoyl chloride, when allowed to react with methanol, produces methyl benzoate. It can be retrosynthetically represented as methyl benzoate, retrosynthetic arrow, benzoyl chloride plus methanol. That means methyl benzoate can be made from benzoyl chloride and methanol. Disconnection. It's an analytical operation which breaks a bond and converts a molecule into possible starting materials. This is the reverse of a chemical reaction. It is represented by a retrosynthetic arrow and a curved line drawn through the bond being broken. For example, paracetamol. It's an amide. We can disconnect this amide bond like this to get the starting materials, 4-aminophenol and acetyl chloride or 4-aminophenol and acetic anhydride. Functional group interconversion. Sometimes what happens that the disconnection of a bond doesn't lead to the logical starting material. In that situation, one functional group is replaced by another to make the disconnection possible. The operation of writing one functional group for another so that disconnection becomes possible is called functional group interconversion. It is represented by a retrosynthetic arrow with FGI written over it. For example, replacing aromatic amine group with nitro, as amine can be obtained by the reduction of nitro. replacing aromatic carboxylic acid group with aromatic methyl, carboxylic acid with nitrile, primary amide with nitrile, amine with imine, primary amine with azide, amine with amide, amine with nitrile, carboxylic acid with alcohol, diol with alkene, keto with alcohol, etc. Let's have an example where we can see the significance of functional group interconversion. Suppose we have to do the retrosynthetic analysis of 3-bromoaniline. Here we cannot get it from the bromination of aniline because amino group in aniline is orthopara directing. So we can say that the disconnection of CBr bond is not possible in 3-bromoaniline. But if we do functional group interconversion of amino to nitro group to get 3-bromonitrobenzene, the disconnection of CBr bond is quite possible because we can get 3-bromonitrobenzene by the bromination of nitrobenzene using Br2 FeBr3. Further, we can disconnect this CN bond because we can get nitrobenzene by the nitration of benzene with nitrating mixture. Thus, we can start the synthesis of this compound from benzene. The first step is nitration to get nitrobenzene. After that, bromination to get 3-bromonitrobenzene, and then reduction using iron and ammonium chloride to get target molecule. Synthons and synthetic equivalents. Synthons are the idealized fragments resulting from the disconnection. That is, the fragments resulting from the breaking of CC, CH or CX bond. They generally bear positive or negative charge. These are not actual reagents. Synthetic equivalents, also called reagents. These are the actual compounds that are equivalent to synthons. Basically, they act as sources for the synthons. For example, if we have to do the retrosynthetic analysis of 1-methyl-cyclohexanol, we can do disconnection here to get hydroxycyclohexane 1-ileum cation and methyl carbanion. These two fragments will be called as synthons. The actual reagent for the carbocation is cyclohexanone, and the actual reagent for methyl carbanion is methyl magnesium bromide. Thus, cyclohexanone and methyl magnesium bromide will be synthetic equivalents. We have just seen that disconnection generally gives positively charged and negatively charged fragments which are electron acceptors or electron donors respectively. Based on that, we can classify synthons as acceptor synthons and donor synthons. Let's take one by one. First, acceptor synthons. These are positively charged fragments. They act as electrophiles. Let's have examples of some acceptor synthons and their corresponding synthetic equivalents. Synthetic equivalents for alkyl cation are alkyl halides or mesylates or tosylates or tripletes. For aryl cations, aryl diazonium salts, fluoro or chloroarenes. For oxomethylum ion, NN-dialkyl formamide, alkyl formate or Willsmere salt. For oxoalkylium ion, NN-dialkyl amide, ester, acyl chloride or anhydride. For hydroxyoxomethylum ion, carbon dioxide. For hydroxymethylium ion, formaldehyde. For hydroxyalkylium ion, aldehyde. For hydroxydialkylmethylium ion, corresponding ketone. For 2-hydroxyalkane 1-helium ion epoxide, for the beta carbocation of ketone or ester, alpha beta unsaturated ketone or ester, for the beta carbocation of nitriles, alpha beta unsaturated nitrile, for alpha carbocation of ketone or ester, alpha chloro or alpha bromo ketone or ester, for alpha carbocation of secondary amine, iminium ion that can be generated in situ by the reaction between formaldehyde and secondary amine. Donor synthons. These are negatively charged fragments. They act as nucleophiles. Let's have some examples of donor synthons and their corresponding synthetic equivalents. Synthetic equivalents for alkyl anion are Grignard reagents, alkyl lithiums, or Gilman reagents. All these three can be derived from alkyl halides. For the aryl anions, Grignard reagents, aryl lithiums, Gilman reagents, and aryl boronates. All these four can be obtained from aryl halides. For alkenyl anion, the synthetic equivalents are alkene, alkenyl halide, and alkenyl boronates. For acetylide, lithium, sodium, or copper acetylides that can be generated from terminal alkynes. For cyanide, sodium or potassium cyanide. For enolate, ketone or beta ketoester. For cyanomethyl anion, acetonitrile or cyanomethyl ester. For nitroalkyl alpha anion, nitroalkane. For acyl carbanion, 1,3-dithione or nitroalkane. For wittic elite, alkyl phosphonium salt. For sulfonium elite, corresponding sulfonium salt. For sulfoxonium elite, corresponding sulfoxonium salt. Guidelines for the disconnection. The most difficult part of a retrosynthetic analysis is to find the bond to be disconnected. Here, we will discuss some guidelines to help you out, but the best way to learn is through experience and practices. The overall aim of retrosynthetic analysis is to get back to starting materials that are easily available from the chemical suppliers and to do the synthesis as efficiently as possible. Let's discuss those points. Point number 1. Disconnection must correspond to known and reliable reactions. Suppose we have to do the disconnection of this molecule to find the synthons. There are two ether bonds, O-aryl and O-alkyl. If we break O-aryl bond, we will get rhenium ion and alkoxide ion. If we break O-alkyl bond, we will get phenoxide ion and carbocation. The reaction between these two fragments involves aromatic nucleophilic substitution, which is not feasible, while reaction between these two fragments involves SN2 reaction, which is feasible. So we will disconnect O-alkyl bond for retrosynthetic analysis of this molecule. Point number 2. For compounds consisting of two parts joined by a heteroatom, disconnect next to the heteroatom. Suppose we have to disconnect benzyl phenyl ether to find the synthons. This molecule has two parts, benzyl and phenyl, connected to each other through oxygen atom. If we disconnect this carbon-oxygen bond, we will get synthons, phenoxide and benzyl cation. The synthetic equivalents will be phenol, and benzyl bromide respectively. Thus, if we allow phenol to react with benzyl bromide in the presence of a base like sodium ethoxide in ethanol, benzyl phenyl ether will be produced. Point number 3. Consider more than one disconnections and select one that avoids chemoselectivity issue. For example, suppose we have to do the retrosynthetic analysis of 3-hydroxy-1-phenyl butane 1-one. We can disconnect here to get these two donor and acceptor synthons. Let's label it as path A. It's hard to get such donor species, so we will do functional group interconversion of alcohol to keto group to get the real donor, which is enolate. The synthetic equivalent of this enolate will be acetone. The synthetic equivalent for this acceptor will be benzoyl chloride. If we disconnect here, we will get hydroxyethylhelium ion as acceptor and this enolate as donor synthons. Let's label it as path B. The synthetic equivalent for acceptor will be acetaldehyde, and for enolate it will be acetophenone. Now, if we follow path A, we will take acetone and then allow it to react with LDA to generate enolate. The enolate will be allowed to react with benzoyl chloride to produce 1,3-dione compound. Now, chemoselective reduction of left side ketone will give target molecule. If we follow path B, we will take acetophenone and then allow it to react with LDA to generate enolate. The enolate will be allowed to react with acetaldehyde to produce target molecule. Here we can see that path A requires chemoselective reduction in one of its steps, while B is free from such type of chemoselectivity issue. So, disconnection shown in path B is better to follow. Now let's do some exercise. Suppose we have to do the retrosynthetic analysis of this molecule. One of the strategies will be disconnecting ether linkage. There are two ether bonds, left and right. If we disconnect left side ether bond, we will get allyl cation as acceptor synthon and alkoxide of 1,2-diol as donor synthon. The corresponding synthetic equivalents will be allyl bromide and 1,2-diol. Here we can see that if we allow these two fragments to react under basic condition, it might be hard to control the regioselectivity because we want selective alkylation of primary alcohol in the presence of secondary. On the other hand, if we disconnect right side ether linkage, we will get 2-hydroxycarbocation and alkoxide ion of allyl alcohol as acceptor and donor synthons respectively. Their corresponding synthetic equivalents will be epoxide and allyl alcohol. If we allow these two compounds to react in the presence of a strong base, the epoxide will be opened up by alcohol regioselectively from the less hindered side to give the desired molecule. Thus, the synthetic route will be reaction of allyl alcohol with sodium hydride to generate sodium alkoxide, followed by reaction of this alkoxide ion with styrene oxide to give desired product. Let's have another molecule for the retrosynthetic analysis. The molecule is ethyl N-butylamine. This is a secondary amine. If we disconnect CN bond of ethyl side, we will get two synthons, butylamide and ethyl cation. Their synthetic equivalents will be N-butylamine and ethyl iodide respectively. But there is a flaw in this synthetic route, because when we allow N-butylamine to react with ethyl iodide to produce ethyl butylamine, the product formed is more reactive than the reactant amine itself. So it will undergo further alkylation to produce tertiary and quaternary amines as side products. To overcome this problem, we will do functional group interconversion of amine to amide and then disconnect this amide bond to get butylamide and acetyl cation as synthons. Their corresponding synthetic equivalent will be N-butylamine and acetyl chloride. So the synthetic route will be acetylation of N-butylamine to give secondary amide and then reduction of this amide by borane to give secondary amine. We can do retrosynthetic analysis of this compound differently. In this, we will first do functional group interconversion of amine to imine. The disconnection of this bond will give these two synthons. Their corresponding synthetic equivalents will be butylamine and acetaldehyde. Thus, the synthetic route will be reaction of butylamine with acetaldehyde to form imine and then reduction of imine with sodium cyanoborohydride to produce secondary amine. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.